Hello everybody. In this module I'll be discussing this published paper that implements a support vector machine in order to predict storm surges. Although given the amount of time, we would not be able to cover all the technical details of this paper, but would concentrate mostly on the overview and how in general the method has been implemented and how it differs from more traditional numerical or predictive techniques. A support vector machine is essentially a machine learning algorithm, and this is why this paper is unique, where it tries to implement a machine learning algorithm as compared to deterministic, more traditional numerical algorithms. And in this case, it's a continuous time data, and hence uh, it has been tagged as support vector regression. We'd start off with the definition of a storm surge. Essentially, during a storm, when high winds push on the ocean surface, we see that there's a significant increase in the water level beyond that of the natural sea level, and this is caused due to the invading winds on the ocean surface. This rise in water level is termed as a storm surge. Given the amount of destruction that it actually causes in the surrounding areas, it is imperative that more robust and predictive modeling techniques be devised in order to predict these increase in water levels under catastrophic conditions. The contributing parameters that affect storm surges are generally pressure, wind velocity, directions, and tide patterns. We have seen in the past that existing numerical techniques have been leveraged in order to come up with better finite volume or finite element methods that performs direct numerical simulations over a full Navier-Stokes solver. However, they prove to be very computationally challenging and have a very high algorithmic complexity, often not in polynomial time. This calls for predictive models that may be less challenging than a Navier-Stokes solver, and previous literatures have gone through a neural net based predictive model where the input data is basically the contributing parameters, and the recorded data of storm surge levels are my output classes. The neural network trains on these data and tries to come up with a nonlinear model that actually fits these four contributing parameters in this case, and predicts a new storm surge levels in case of a new incoming storm with different high pressure values, velocities, and so on. However, neural networks often face the same problems as that of a Navier-Stokes solver. It is a computational challenge to implement a very efficient neural network, and they often suffer from underfitting or overfitting issues, which will be discussed in the next slide. In this paper, the authors have tried to implement a support vector machine in a continuous time sense. It is often called a support vector regression and has fundamental similarities with linear regression algorithm that we have all seen. A linear regression algorithm is essentially an optimizer that minimizes the squared error between the predicted values Tn, which can be a linear straight line or a linearized polynomial or some form of polynomial in general, and it does that by optimizing over the basis vector w. In case of a support vector regression, it is somewhat similar, but at the same time not exactly the same as that of linear regression. It does not minimize the squared sum of the errors. In fact, it minimizes w over the cost function, which is essentially an epsilon insensitive error function. The objective is to come up with the values of c and w that minimizes the cost function given on the right. In linear regression, we often see that the model suffers from overfitting or underfitting issues. Overfitting is basically when your model has captured the given data set really well, but predicts really badly for newer data sets. So it has basically memorized the idiosyncrasies of the given data set. While in case of underfitting, it does not fit the data well and neither does it predict well. So we're trying to look for a trade-off between underfitting and overfitting and hit the sweet spot, which is just right, and come up with a model that does more or less well for the given data set and predicts efficiently for newer data sets as well. But it is often a pain to come up with this sweet right model that um, predicts newer data sets, and hence linear regression is often not the best algorithmic choice for machine learning. In case of support vector machines, we are actually not solving for a polynomial or a line. In fact, we are solving for a region in space that best optimizes this cost function. So we are solving a quadratic optimization problem subject to to these two conditions, which basically reduces the error until it has become more than the epsilon value. In two dimensions, this line the line is basically a y equals mx plus c kind of line, but in higher dimensions, it's basically a hyperplane. But as is evident from the picture, it is a hyperplane and not a surface. And the idea that support vector machines are linear comes into the picture here. In general, it's not so, especially for this problem where the input parameters and the output data are highly nonlinear. It is imperative that we come up with a model that captures the nonlinearities as well. In fact, it gives us some idea of a very high dimensional surface that can regress over the given data set. For this, the authors have used a kernel trick for nonlinear support vector machines. Uh, what it essentially does is tries to capture the nonlinearities in the data by a suitable transformation into a high dimensional basis set. So uh, the inner product in x and y can only be taken when they're linear, but it can be done if they're nonlinear. So basically, they convert x and y through a suitable transformation to phi x and phi y, and in this higher dimensional basis set, we have px and py to be linear. And this way, we can compute the inner product between px and py. So basically, the wx, the inner product between w and x that has been shown in the constraint conditions, and now is transformed into w and phi of x, so that inner product between the transpose of phi of x and w can be computed in order to solve this quadratic optimization problem. Based on this technique, they've come up with a predictive support vector machine and have compared the values, the storm surge levels, for two data sets. Both of them have been taken from the Longdon station in Taiwan that experienced the Eri typhoon, and they show quite remarkably well predicted values given the data set that was taken for almost 48 hours. Uh, in both the cases, we see that there is a drastic uh, decrease in the mean square error. RMSE stands for root mean square error, and we're trying to find out the basis vector for the best value of C that minimizes the RMSE. We see in the first case, in which where the kernel transformation function has been chosen to be a spline, the RMSE goes down to 0.05 for a value of C which is equal to 10, while in case of the RBF based kernel transformation, the RMSE values goes down to about 0.015 for a C value of 2. So this essentially shows us that the predicted results are actually quite close to the actual results. In conclusion, this paper implements a new support vector-based regression algorithm to predict water rise levels, which is essentially a storm surge problem. It shows us the accuracy of the model is remarkably high and is often better than previous literatures that have reported neural network-based predictions. In fact, the paper goes on to compare the solutions with traditional numerical DNS solvers for Navier-Stokes, and they show that all the predictions are not as accurate as that of a DNS solver, but are quite good in comparison to deterministic algorithms, and hence is a good choice for a machine learning algorithm to predict storm surge problems. And that's it. Thank you.